from the negative over to the positive. Then we have that path for those electrons to flow. So what's going to happen is the atom that's closest to this battery, the positive terminal on the battery, will lose one of its electrons, and it will come over into this region here. It's being attracted by unlike polarities. Well, now we have an atom here that lost one of its electrons, and for it to be an atom of copper, it has to have that same amount of electrons in it. So it's missing one. So what it's going to do, it's going to pull one from over here, another electron. And it's going to be a chain reaction, because we're going to start pulling these electrons out of the negative side and transferring them over to the positive side. We have a flow of electrons. We have current flowing. We have some charge going through this piece of wire, but it is unlimited. It is as fast as these electrons over in the negative side of the battery can flow over into the positive region of that battery. So it's just totally uncontrolled. It's as fast as this thing is going to go. As fast as the wire can handle, as fast as physically possible from one electron to bounce from one side to another. So we have to do something about that. We have to control that. So there is a device or a substance called resistance. It's a measure of the opposition to current flow in an electrical circuit. And right now, as this stands with a wire between negative and positive, there's no control, there's no restriction, it's unlimited. So what we're going to do is we're going to open this circuit, we're going to break that circuit, and we're going to put a resistor in here. Symbol for a resistor. We're going to limit the amount of current flowing from the negative side to the positive side. That's how we control that. The more resistance we put in there, the less current flow that we have going through this circuit, this little complete circuit from negative to positive. The greater the resistance, the less flow we have in there. The smaller the resistance, the more flow that we have going through that circuit. To measure the current in a circuit, you will have your multimeter. There's your little display on it, little selector knob. You've got some jacks on the bottom of it. We have to set your meter to where the flow of electrons are actually flowing through the meter itself. So that means we have to open the circuit. We have to break it. We have to open that up. We have to disrupt the charge of electrons that are going through there. And we have to divert that flow of electrons through your multimeter back into the circuit again to start them flowing again. So we have on your meter, or you have, a common port, usually indicated by a black port right there. We will put this one because we have to observe polarity. We have to put the negative to the negative and the positive to the positive. So we're going to put this common lead over to the circuit where we open it up, and then your positive, I think it's right here, milliamps. This red one, we're going to connect to the positive side of your circuit. And now what you did, and this is also going to have to be selected for, on your meter, milliamps, because that's our world. We work in very small current flows. This will be in milliamps, and there'll be some number displayed up here which indicates the amount of current flow going through your meter. But we have to put your meter as part of the circuit so that when these electrons leave the negative region of that battery, they flow through your meter. They'll actually go into this lead, flow through the circuitry so we can get an accurate measurement, and then we'll come back out this lead and go back into the circuit and complete the circuit over to your battery. And that's how we measure current. We measure current as putting your meter as part of the current flow going through the circuit itself. Now on your vocabulary, you also have one. So we've covered resistance and we've covered current, but we haven't covered voltage yet. Voltage is described as a quantitative expression of the potential difference in charge between 2 points in the electrical field. A lot of words, isn't it? So we're going to get your meter again. The units of measurement in voltage is volts. That one makes sense, doesn't it? So we're going to set your meter up now, and we're not going to use the milliamp reading. We're going to use the voltage reading, and we're reading DC, so you should see a V with a line over the top of it on your meter. And we still have to observe polarity. So we're going to put the common lead, the one that's usually indicated by a black coated jack, we're going to put that one on the negative part of our battery. And the positive one, which is indicated by V, on the positive side. And what we're doing is we're measuring the amount of potential in between these two sides of the battery. As we lose more electrons flowing through this circuit, and we can measure them, we can also see that the charge going in between these two, the positive and the negative, is actually being reduced. We're losing the ratio of positive to negative particles over here, because these negative particles, when they go over to the positive side, are neutralizing themselves. It's neutralizing each other. So the potential difference between one side, the positive side, and the negative side is actually being reduced. The common term for that is, I have a dead battery. That means as many electrons that have flowed from the negative side to the positive side has reduced to almost nothing. There's no charge or difference in potential across the battery anymore. And that's measured by checking the voltage between the positive and negative side of the battery. I hope this makes a mental image. You've heard of the mind's eye. A lot of times in our field, you have to be able to visualize what's happening, because you can't see it. It's nothing that, you can't see these electrons moving in here, but if you have that visual of what's actually happening inside your head, you can make more sense out of, how do I read current? I have to read current by actually rerouting that path through my meter and actually measuring the flow of electrons. When we're measuring voltage, I'm measuring the potential difference, how much difference in negative and positive ions or particles are in between these 2 points. We could actually measure the voltage across that resistor by the same procedure. We could put our meter leads, move them from here, and put them across that resistor and see what the difference between positive and negative on that resistor is. We call that a voltage drop. It's how much are we reducing the voltage between here and here? How much are we reducing the current flow from point A to point B, from negative to positive? In a circuit like this, we're going to start off by using Ohm's law. Ohm's law has been around ever since I have, or probably the beginning of time. And it's a little triangle. It's showing a relationship between voltage, current, and resistance. This is one you're going to need to memorize. Some things we just have to know. Something is instrument techs or EPC techs or whoever. We just have to know Ohm's law, because it's a standard. It's a proven thing. And it is the relationship between voltage, current, and resistance. You will see this over and